there are certain devices which actually has the provision for measuring the spectroscopic data, okay, for UV, visible, as well as IR. Okay, you know, infrared basically has got three regions. Okay, this is near infrared, far infrared, okay, and mid infrared. Okay, near, mid, and far infrared. In any device, it's coupled with UV visible spectroscopy. Okay, basically will have a range of near infrared. Okay, so this 3D techniques might come together. The basic understanding of these three techniques is the same. How is the instrumentation, how does it work, and so on. It remains the same, doesn't have much of a difference. Okay, if one understand one, the other one should be more or less easy. Okay, so what kind of lamp will actually generate an IR signal, a visible signal, a UV signal is something which I'd like to explain in this particular section. Okay, so spectroscopy, if I say, what we do is we investigate, okay, the interaction. So what happens is if you have any kind of electromagnetic radiation, okay, falling on a matter, how does it interact? Is it getting absorbed? Is it getting reflected more? Or is it not interacting with the matter? Everything comes under something which we call it spectroscopy. So investigating the interaction of electromagnetic fields, okay, with matter. This is something which we can say about the basics of electromagnetic basics of spectroscopy. Okay? And if we actually want to divide this spectroscopy, what we can do is we can actually divide them into two categories. Okay? So let's just write down the first category. There are different ways of doing it. Okay, you can find different books dividing them into different ways. But you know, broadly classified, these are the two categories which are important. Okay, the first is technique based on energy transfer, okay, between photon and sample. So you have a sample and you have some electromagnetic radiations falling on it, and you know electromagnetic radiation means photons, right? So the photon will actually fall on that sample. How is the energy transfer based on this? The idea is okay? That is the first technique. Okay. The second technique, which is more obvious, and this is something which you also observe in our day-to-day life. For example, if you're basically going to talk about the dispersion of white light into 7 different colors when it passes through a prism, is something which can observe visually. But then that is also nothing but spectroscopy. The technique is dispersion, right? You don't really know how much energy is getting transferred there, okay? But we do have a visual picture of that. So similarly, something like this, we talk about reflection or refraction, okay, or diffraction, okay, dispersion, okay, that is something which we see the 7 colors, okay, because of the rainbow or okay, dispersion, and then we have got something which we call as scattering, okay. So these will actually happen from the sample, okay, and they will actually alter, okay, the amplitude. What it will change? It will alter the amplitude, okay. It will change the phase, okay, phase angle. It can also create polarization effect, polarization, okay, or direction of propagation, okay, a direction of propagation of EM radiation. So you have white light falling, that is an electromagnetic radiation. It basically, let's say, falls on a mirror, it will get reflected, okay, falls on water, it will partly get reflected and refracted. These are nothing but change of direction. And if there is a refraction and reflection happening at the same time, we know that there is some kind of polarization also happening. So both of them are more or less connected. And at the same time, it can actually change the amplitude. So if we have a white light and it gets separated into 7 different colors, the chances are all of them will have a separate amplitude, frequency, wavelength. Okay, you know, red and violet will have different wavelengths. So it is getting separated. Change of phase angle is also very much possible. Okay, so these are the two categories of spectroscopy. So the instrument that we use, basically, let's say, for example, the UV visible spectroscopy will actually come under this first category. What happens is, in general, okay, I think this idea is quite logical and we all know it. We have got two energy levels, okay, and we have got some atom or molecule or electron gas, and then we have got some radiation falling. Now, because of this radiation, if this energy of this radiation, which matches the gap between E1 and E2, okay, and we know that E2 is greater than E1, and eventually, after it relaxes, it will actually come down and it will emit some kind of radiation, right? And if we can actually analyze this radiation compared to this radiation, we can actually find out a lot of information in how much time it is coming out. Is it giving out any kind of visible light? That means luminescence property. We can say it's a luminescent material. If not, it is not a luminescent material, and so on. Okay, and these will depend on what is the energy gap. So these interactions will actually give us more information about the internal property of the. So this is the basic idea, and this is something which you have already learned in the PPTs that you have seen before. Okay, let's try to define some property. Okay, let's try to just write down some properties here. Okay, so these spectroscopic techniques that we are talking about is actually simple. Okay, they are versatile, can be used for different purposes. Okay, they are versatile. At the same time, they are fast. Okay, it does not take that much of time. So if you're doing an XRD characterization, it takes time. SEM takes time. Okay, if you remember that graph, characterization with time. Okay, it is time consuming, other techniques, but this is not. But at the same time, it doesn't mean that it's fast and not accurate. It's accurate. Okay, and affordable. So if you have a UV visible spectroscopic instrument, let's say around affordable in the sense that it is affordable comparatively. Let's say it's around 10 to 15 lakhs. But if you at the same time purchase a SEM instrument or a XRD, it will actually cost you more than 1 crore. So it's totally different here. To analyze, it basically can analyze a liquid sample. Okay, and I'm talking about all three of them: UV spectra, visible spectra, IR spectra. It can actually analyze a liquid element. It can actually talk about gases. It can analyze gas, and it can of course analyze solids. Of course, the setup is kind of different, but then it can analyze all three of them. And I think we should also know the range that is being used. Okay, and I think this is already known to you, but let me just write down this for a typical instrument. So if you have a UV visible IR spectra instrument for the UV, okay, the range within which the radiations are allowed to fall is 300 to 400 nanometer. So there are certain bulbs, okay, certain elements which can actually emit radiation in that particular range. Of course, invisible to our human eye. But then if you talk about visible light, we usually use tungsten lamp, okay, and that visible light, basically used from 400 to 765 nanometers. Might be thinking that why visible light to 765 and not 700, which is something which we have mostly studied. A simple reason is, as soon as it becomes 701 doesn't mean it will immediately become higher. Not that way. You know about it. It's like there is a smooth transition. So even up to 765, you'll be getting a part of the visible light. Even after that also, a part of visible light will always be there. If you until and unless you go to a very higher range. If you go around 800, entirely most of the part of the visible part is gone. Okay? So from 765 more or less, you might have some strong IR signals. So 765 to 3200 nanometer would be IR. Okay, and this is not exactly IR beyond. This would be near IR. Okay, near infrared region. Now, if you go above that, okay, we cannot have far IR and mid IR incorporated along with UV visible because IR radiation generates a lot of heat. Okay, so such devices needs to be made separately. So most of the commercial devices that we have will only have UV and visible. Because IR, if you just study up to this range, you might not have enough information. If you want to know the entire information, you have to take a larger range. Okay? So that's why these devices are sometimes separate. But the working principle more or less will remain the same. So this is actually UV visible spectroscopy. Okay, and why this is more important to understand the optical characterization. In the next class, something which we have already done a bit is the principle. Okay, But apart from that, we are also going to look into different kinds of instrumental setups. Okay, how does it determine the energy level? How does the UV visible spectra looks like, and so on. Okay, so these things which we are going to study. Okay, once we understand the principle why the devices is designed in such a way, why the instrumentation has. What we have is a light beam. Now this light beam might be a UV, might be a visible source, or might be an IR source. Okay, and it will basically fall on the object. Once it falls on the object, we basically have a signal, and that signal might be of different wavelength depending on what kind of radiation has fallen on the sample. And these wavelengths will be reaching the detector, and finally we'll be actually analyzing of this. Okay, and if this wavelength is measured, okay, it will give us a lot of information. Okay, and mainly, okay, this wavelength is measured. Okay, if this wavelength the information that we actually can have, we can actually have information on the chemical structure. Okay, and of course the number of molecules. So it's not that you'll be having an information of the chemical structure only by using UV light. You might be needing IR to fall on the sample, and you'll have more information. And then we are just combining everything together and giving a general overview. Okay? So UV might not give you any information about the chemical structure, but IR will. So the working principle will more or less be the same. Okay, so it can give you a quantitative information. Okay, so it can give you something like a band gap, which is a quantitative information. Okay, and it can also give you some qualitative information. For example, if the sample is opaque or transparent, okay, those kind of information can also be there. Okay? Things can also be gathered. So these actually are main information which you actually are looking for any kind of material. The main aim of any characterization technique is to find out information about that material. That is exactly what we are trying. Okay? So what happens is if we are actually having the absorption of incident energy, so because these electromagnetic radiation will have some kind of energy, and if they are absorbed by a system, okay, it will actually promote the electrons, okay, mostly it's the electrons, okay, depends on how much actually the electron will actually go to the excited state. Uh, the excited state that we usually have, it is more of the chemical part of the system, is basically called the anti-bonding orbital. Okay, so if we talk about this is basically nothing but the in the anti-bonding orbital, the electrons somehow have this nature of having greater energy. Okay, so these are the anti-bonding orbitals that we are talking. So that's actually the main part of how exactly it works. And based on this, we can actually get a lot of information. Now, something which we have not done this till now is something which we're going to discuss now. Okay, and before that, for this transfer to occur, that means the electron will actually go from the ground state to the excited state or to the anti-bonding orbital. I'll slowly tell you what is anti-bonding orbital and how we actually define it. Okay. So basically, for this transfer to occur, uh, match. So if the energy level is higher, you need more energy for transferring the electron. Okay, so that means whatever energy is of the incident photon must be enough to actually make the electron transfer from the lower orbit to the excited state. It should indicate, and can say it should match the energy, okay, get by electron. So what to be promoted? The energy is low, okay, the incident photon doesn't have that much energy, the electron won't get transferred. Okay, there will be some non-radiative transition maybe, but what happens is the electrons will just get excited and come back to the ground state, okay, without giving much of an output because it doesn't have anywhere to settle down for a moment, okay. It directly comes down. So based on this, we can actually say, and this is actually important when you write out any kind of maybe publication or information or research, okay. Basically, we can say there may be three types, okay, three types of ground. Generally, any kind of material is there if you are allowing an invisible IR or a visible light to fall on the sample. There will be three types of ground state. Ground state orbital. And so there are three types. And what are those? Okay. The first one is basically called as sigma. So I just write down the symbol, but then and when you explain your research based on these ideas, this is actually very important. It's basically called the pi bonding. Okay. So you know there is sigma bonding, there is pi bonding in molecules. Okay, and those actually are represented by this. Finally, the third ground state that you usually have is the N bonding. So N bonding, when you do it, you see that it doesn't have, you don't find it in too many cases. Pi bonding and sigma bonding are important. So you can see pi and sigma are talking more about the molecular bonding, and N bonding will actually talk about the atomic orbital. Okay, so this part is actually your sigma bonding. Okay, this is pi bonding, and this is N bonding. Just to remember these. So if there are bonding states, the electrons will actually go into the excited state. So there should be certain anti-bonding states as well. Okay. So let's just look into some anti-bonding states. There are two, in fact. Okay. So besides the um, anti-bonding orbital, or like this, anti-bonding orbital. So the anti-bonding orbital are, there are two. Okay? Both of them are actually represented by star. Okay, so I'll just write down number one, sigma star orbital. Okay, orbital. So these are actually termed as anti-bonding orbital. Okay. So you know, in your class 12 or 11 chemistry, basically you also study about the sigma bond and pi bond. Okay, and this is something which we have seen. So this is your sigma star. Okay, and this is your pi star. So there are two pi orbitals, the sigma star orbital and the clearly. So these are the two anti-bonding orbitals. So whenever we say that there is a transition happening, technically we need to think of pi orbital and the sigma orbital and so on. Okay. So whenever we are saying that there is a transition, okay, in general, I will just draw a figure which will make it more clear. Probably if you don't remember the sentence, if you remember the figure, what happens is we also call this as S bonding orbital, which is the sigma orbital. Okay? The sigma orbital is also called the S bonding orbital. Sigma, okay, I will just write down all the different ways of writing it. I'm just writing out all the options so that you are not confused. Anti-bonding orbital means you are thinking an asterisk. So sigma orbit anti-bonding means sigma star. Okay? Sigma to star transition. So there are these transitions which are happening. Okay. So if I just complete this, okay, I will just write it down as sigma bonding orbital. So if I write down sigma anti-bonding means sigma star. Okay. So that means we are talking about the S bonding orbital means we have got a transition from sigma to sigma star. Okay. Please don't get confused because when I'm writing down this because different books use different notation, and I think we should write down all the notations possible. Okay. So whenever we have got a transition from sigma, okay, to sigma star, okay, it as good as same transition from S bonding orbital to sigma antibody. Both means the same thing, equivalent. So this is important to know. And then you can also get a transition from, let's say, pi to pi star. So that is also possible. So this is basically nothing but excitation of an electron of a lone pair, okay, to our anti-bonding pi orbital. So you understand this is your anti-bonding pi orbital, okay, and it will basically have a transition from the pi molecular orbit to the pi star molecular orbit. Okay, so these transitions keeps on happening, okay, and these transition usually happens because of the absorption system. Okay, so electron transitions, okay, occurring due to absorption. Okay, so there is basically nothing but the absorption that is happening here. That means some external agency is basically imparting some energy. Okay. Absorption of UV, it might be UV and it might be visible, okay, visible light. Okay. R, and what are those transitions that we are actually talking about because of UV and UV visible? First is sigma to sigma star. Okay. And then we might have a transition from N to sigma star. So if you talk about the antibonding orbital, there are two. Okay, and you can have a transition from sigma to sigma star. You can have a transition from the atomic orbital to the antibonding orbital as well. That transition is also possible. And UV visible spectra actually can give those information. And to is possible, okay, then we can also have a transition of pi to pi. So these are the four important transitions that you should actually remember. Okay. And when we talk about something like sigma to sigma star, okay, or n to sigma star, okay, it is actually having a further distance, okay, it is at a larger distance. So what happens is if I take this condition, this will actually require a lot of energy, okay. So this will actually involve, I'll tell you why, okay. It will involve high energy. We will just draw a figure, probably then it will be more clear. Involve high energy, okay, and this will actually occur in UV region, okay, in the UV region of 180 to 240 nanometers. Okay, so you understand this that when we talk about this far UV region, this will have more energy, right? Because if you remember this relation, E is equal to H nu, which is equal to Hc divided by lambda. So if the wavelength is less, the energy is definitely going to be less. So this range, which is actually quite low compared to the standard UV range, okay? And if you remember the standard UV range that we talked about yesterday, 300 to 400 nanometers. If you just go beyond that, okay, if you just go beyond that, some instrument does have this range, you will see that this will actually involve high energy. And if you do that, you're basically going to have these two transitions prominently. This will actually have greater energy for the transfer of the electron from the sigma to the sigma star orbital. Okay? But then, is there an easier way to remember this? Of course, there is. Because this is something which you are all of you have actually come across. Okay? So maybe I can just write down this normal representation. Okay, and let me just draw down the different energy levels. So let's say is your sigma, and let's say this is your pi orbital. Okay, the scaling might not be very correct, but then I think this is acceptable if you're just doing it onto the exam during your exam. Okay, fine. So we basically have got 2 excited states and 3 ground states. Okay, and maybe include this. Okay, so we will just write down this is your energy, this side, and then this is your energy level. It's very easy to understand. The important thing is you should actually remember this for your exam also. And then at the ground state, we have got sigma orbital, we have got the pi orbital, and the n orbital. Usually there is a gap between sigma and pi and n orbitals are more closer to each other. Okay? And then here we actually have the pi star antibonding orbital below the sigma orbital. Okay? So this is something which is okay. So in general, if we actually want to remember this, okay, please remember these two are actually called the bonding orbitals. Okay, I'm talking about the molecules, okay, not about the atoms. So when we talk about atoms, we're talking about N, and this is actually nothing but the anti-bonding. Right? So this is something which we are doing. So this is your anti-bonding. So now what we do, we basically can look into the transition. Okay? So once we have drawn this, maybe we can just do some transition levels here. Okay? This on the other side, because here I cannot draw the transition because it's too heavy. So we have got these levels. And maybe we can just draw some straight lines here. Okay? Easy for you to understand it. Know what these lines will actually represent. Okay? And then if you can remember this figure, I think you can easily explain whatever question is asked, which one will require higher energy and which one will require lower energy and so on. So you can see here, you can actually have a transition from here to here, so possible, right? You can actually have a transition from here to here, possible, okay? You can also have a transition from this level to this level. Okay. And these are actually nothing but the selection rules. It's not that you can have any transition. Some of the transitions are actually not possible and not happening. You don't have a transition from this n level to this level. Okay. Sorry, not from this level. So basically you don't have a transition from this level, okay, from the pi level to the sigma star level, okay, because there is this bonding issue that comes into the picture. So let's just write down these values here. Okay. What are these transitions all about? Okay. So I think you can easily see this. Okay. So if you just look into the transitions here, this is your sigma and this is your sigma star. Okay. So this is basically nothing but a transition of sigma to sigma star. Okay. And then here this is your n. Okay, and that is your sigma star. So this transition is the n to sigma star. Okay. So that's the second transition. Here what we have is nothing but pi to, this is at this level, so this is pi star. So these are the 4 transitions that we were actually talking about. Okay, and 2, 5. Okay. Now 2 of these transitions are something which I said will actually involve a high energy. First one was sigma to sigma star. So this one is one, okay, which will involve some high energy, and another is n to sigma star. So this. Okay. So these 2 will actually involve high energy. Okay. So this, by this color I am talking about high energy. Why? Because it needs to cover greater distance. It needs to cover greater distance. We need more energy for this transition. We need more energy for this transition. But for this particular case, the energy needs to be less. And that is why I said this is high energy. Okay. So what is the wavelength that is needed? You have to just remember this: 1822240. Okay. So if we are actually going into the UV visible spectra, which we have seen yesterday. Maybe you can take a background color, it will be easy for you to see. If you are having a transition at some range between 180 to 200 or 300, okay, there is some absorption happening. That means we may be talking about a transition between sigma to sigma star or n to sigma star. Okay, it depends from sample to sample, so we have to just analyze it. So this is actually about this transition. Okay, so you have to remember these are nothing but the energy levels one side, okay? And on this side we are actually talking about this. So if you are doing it in your exam, I would suggest all of you please do a neat diagram. Okay, I can call this diagram more or less neat, so it should be fine. Okay, if you understand it. Now the principle based on which we can know that how much is the transition that is happening is something which we know already. That's the Beer-Lambert's law. So I'm not going to explain Beer-Lambert's law. Please refer to the previous lecture. We've already talked about this, but I'll just write on one line here. Okay, I'm just not going to repeat anything. Okay, so the absorption of light, okay, of specific wavelength, basically based on, if you just look into their Lambda square, if you remember, it actually depends on how, what is the path length, okay, what is the concentration of the sample, okay, something like A, B, C, and based on this, we are actually going to have the absorption of light happen. Okay. Now this UV visible spectra can actually be recorded by different kinds of devices. Now the point is, what is the device, how exactly does it work, and so on. Okay. So the working principle more or less should be very simple because it's more or less natural. Okay, light falls on a sample, it gets absorbed and so on. So we're just going to look into the instrumentation part now. Okay, and we are just going to look into a bit of more details. And this UV visible, you know, most of the time the UV visible spectrum will be, a spectrometer will be a single device. It might not have an IR because sometimes we need higher energy IRs, okay, which may not be incorporated into the system. So this UV visible spectrum and even the IR spectrum also, okay, will basically be recorded by a device which is having similar setup, okay, and be recorded, okay, via. So let's see what are the devices by which we can actually record them. There are three kinds of devices. Okay, let me just list them one by one. The number one is basically nothing but called a single beam spectrometer. Okay, and then if there is single beam spectrometer, there should be something which is also called a double beam spectrometer. Okay, just a small fact: double beam spectrometer is more popular. Okay, it will be very good information. Have it in our department. We have the setup. There is also something which is called a simultaneous spectrometer. It basically uses a diode. Okay, simultaneous spectrometer will basically use diode. Okay, so we're just going to have a brief look into the construction, and it's not very complicated. Okay, that is basically called a simultaneous spectrometer. Okay, and if we are considering a visible source of lamp, that will be nothing but a tungsten lamp. Okay, so if you consider the main parts of this, okay, the main parts of these, we basically have three. Okay, number one would be the light source, and light source will be different for UV and different for visible. Okay, so UV it is a deuterium source, and for visible light it's a tungsten source. But we'll come to that later. Okay, is going to give you that idea. It's very simple. And there is a sample holder. Okay, the main part which is common to all three of them. Okay, and then finally we have got a detector. Okay, so these parts are common. Apart from that, the construction is slightly different. We'll just grow these. Okay, these parts are all three of them. These are the parts which are there. Okay, and you know these devices. If you just want to construct it on your own, also you can do it. The only thing is whatever instruments or whatever parts you are using needs to be of the highest quality. Okay, so that's possible. Okay, because you know you can go to a shop and buy a tungsten lamp. That's not a big deal. Okay? So we have got these three. Okay, and let's try to make a clear description or a very simple description of all these things. So let's see. So the first one is basically nothing but a single beam UV spectrometer. Okay. So let me not draw the uh, image here, okay, the block diagram. I think you can understand this. Okay. Very simple. First we have the source. Okay. So this will be the source. And we do have a monochromator. If you want to draw a block diagram, you can do it. Okay. You can just simply draw a block diagram. Is there, and then we have got the sample. So if you want to have a specific wavelength of light falling on a sample, we basically use a monochromator. Okay. So monochromator is nothing but to divide the wavelength. So even if you are allowing UV light to fall, and if you want to be selective that I want only this wavelength to fall on a sample, I need to use a special setup, and monochromator is a part of that setup. Okay, a very important part. That is something which actually separates the wavelength. We have got the source, we have got the some monochromator. After you have got a single source of wavelength, you allow it to fall into the sample. Okay, and then once the source crosses the sample, some of it is absorbed or reflected or whatever, and then it is finally done and used in the detector. Okay? So that is your single beam reflector. Okay? Single beam. Basically, we call it as UV visible spectrum. Okay? Second one is basically nothing but the double beam. Okay? And then here I really cannot just do a block. Okay, it's slightly more complicated than this, and maybe we can just enjoy it from this. Okay, so what I will do is I'll probably just try to this, and then we allow light to fall on a beam splitter. So there is something which is called a beam splitter. So you can have a part of the light getting reflected, a part of the light getting reflected, and so on. Okay? And then there are some mirrors. Okay, and these mirrors will allow the reflection. Okay, and then after it gets reflected, it will actually pass through one sample. This diagram probably I have already given, but that was in the form of image which I have copied from Google. Okay. So I would prefer all of you to just practice it once and drawing. And when you are conducting the exam, if I'm asking you to draw a schematic of a double beam spectrometer, probably this is something that you need to do. Okay. So, and for your exam purpose, don't worry, if you don't use the scale, it's fine. Okay. I need a very beautiful diagram. That's not important. The main part and things should be explained. That is more important. I'm using it with the help of a computer with a software, so it's more easy for me. So what happens usually here is basically there is a lamp. So this is a double beam spectrometer, and we have a lamp. That lamp might be tungsten lamp if you are having visible light. That lamp might be deuterium lamp if you want to use UV light. But then everything cannot be simultaneous. Okay, it needs to be part by part. And then we have got the grating. So grating will actually act as a monochromator. It will actually give you the selected wavelength. You remember what is grating. Okay. And then there is a beam splitter. So as the name suggests, beam splitter means it is going to split the ray of light into two sections. Okay, one will be reflected. Okay, and one will be just transmitted. And that is the same. Both the light will be having definitely the same wavelength because we have already selected the wavelength of the beam part. Okay, and then what happens is this will be actually a reference cell. Okay, this is basically called as the reference cell. So see, I'm not going to give you how to do the writing part. I think it's easy. Okay, but then you should be able to write it down on your own. It should not be very complicated. And this is basically the sample cell. Okay? And then you have got detectors. Okay, so let's say this is a detector here, and this is another detector. I'll tell you what is the importance of reference cell and sample cell. If you don't remember, I've already told you this. But anyway, this is detector. Let's make it detector 2, and this is detector 1. Okay. And then we have got the amplifier and the uniform digital signal transformer, whatever we use. Okay, let's say a differential amplifier. So I'll tell you what is a differential amplifier being used. Okay, so now look into this now. This is basically nothing but your double beam. Okay, so this is the schematic of the double beam. So what happens usually is you have your sample here, okay, and then it is placed inside something which we call as cuvette. Okay, so what do you mean by cuvette? Basically, it's nothing but holder, sample holder. Okay, so what happens usually is that a cuvette mostly is made up of quartz. Okay, why? Because UV light is actually absorbed by glass. So this is something which you should know. Made up of quartz, because UV light is absorbed by glass. So if I have a sample inside a glass sample holder, the UV light will be absorbed and it will reach the sample. You're not going to get any signal in the detector because of the sample. So I don't want that. So most of the time it is made up of quartz. Okay. But then there might be some signal, okay, which may be because of the cuvette, okay, because of the environment. I don't want that. That's why a reference cell is put. So whatever signal I get finally, okay, should be only because of the sample which is inside the cuvette, okay, and not anything because of the environment or because of the sample holder and so on. So that's why a sample holder is placed here, the reference cell, which is more or less empty. Okay, this does not have anything. This is empty, and this will actually give you a signal, and this will give you a signal along with the sample. So the differential amplifier is used to subtract this signal from this signal, and finally whatever result you are going to get is going to be the signal only from the sample. Okay? And this is what we need to study, and that is why it is actually used. Okay? So it's important that we understand why we are actually double spectrum. So this is a double spectrum. Okay. So next, what we have is basically the third one. Okay, and the third one is kind of okay. So let's just look into the third one. Third one is basically called as a simultaneous beam. Okay? So I'm not going to show any picture here. What we have is a source. Okay, and then we actually have a sample, and then we actually have a detector which is kind of different from whatever detectors we are using now. Okay, so a detector is basically made up of diode. Okay, so diode is a detector. So it's a diode is a detector. So that is basically nothing but simultaneous. So simultaneous. So this simultaneous beam data is actually very efficient. Okay, nowadays it's being used. Okay, why? Because it is very fast. Okay, it gives the result very fast. And diodes, are very good sensors in a way. Okay, detection of absorbance, okay, of all wavelengths. So it basically can do this detection of all wavelengths and separate them out very fast. Okay, so this is basically faster and fastest and most efficient. And this is actually used a lot. Okay, so that's actually a very important thing to understand. Let's just look into the basics of instrumentation. Okay, I think that is very important. Okay. So we'll just look into some important points. So I'm trying to complete this class itself. So let's not go into the next class because it's very difficult to confusing. So you have to just think about the last class. We have got the light source which I open already. Okay. And you basically have got UV. So we have got a tungsten filament for UV. Okay? Sorry, not for UV. This is visible light. exactly do we use for UV light? It will be deuterium, okay, or even the hydrogen lamps. Hydrogen lamps. So if you have hydrogen lamps, it's the same UV that comes from the sun, okay. Basically, the same UV that comes from the sun. So we have this in the hydrogen lamp. Okay? So this tungsten filament that we are talking about, which is the visible light, okay, it basically will be ranging in the nanometer. Only for the UV source, okay, depending on how much temperature it has, it will really give you the visible range, okay. But then if you're giving more temperature to it, it can also go into the near infrared range. So this same tungsten filament can also be used to generate the IR range, okay. But usually it's not done, okay. The IR is actually a separate device many of them. Okay? And then 160 to 375 will be the wavelength range for the light source. So you have to just remember this, okay? And then I go to this more compare the previous mode or instrumentation that I will look into the instrumentation part. I'm going to write on this. So this and finally, we have got the sample stage, and you see that how the samples are placed, okay, depending on what kind of detector you are using, is it double beam or a single beam. We have got the detector. So these are common, okay. So detector might be mostly, okay, you know, there are new technologies coming up, but conventionally it's a photodiode or a CCD. So CCD is not mm, passive operative, okay. It's a charge coupled device, okay, charge coupled detector, okay. So we use that also as a detector. So actually very sensitive, they are visible. A very important note that is basically nothing but so QVets are something where the reference, okay, and sample solution, okay, containers. They are basically nothing but where the sample solution and samples are taken, okay, and basically have to be transparent. Okay, so as I told you, it needs to be transparent to the deficiency solid. A glass is not transparent to UV. Okay, so inside your home you have glass inside a glass chamber. Usually the UV radiation will stop, not totally but mostly. Okay, and we need that because you know we cannot stop it totally. That's very difficult. Okay, so we just need to allow all the UV radiation falling on the surface. That's why we cannot use it for glass. Okay, so transparent towards passing. So maybe I can just work on this since I told this. Arch is transparent. That's why this particular QF is being used. Okay, so that's the info. So that's it for UV visibility.